Hello everyone. In this video we are going to talk about the three different coordinate frames that you'll see in finite element analysis: global, local, and natural coordinates. So to motivate you why we need different frames, let's start with a truss example. So one of the elements that you see frequently in engineering is a truss to carry loads for you in bridges, in roofs, and so on and so forth. So if you have a truss like this one in this picture, and you have some external loads like applied at nodes B, C, E, and some boundary conditions at A and D, right, a pivot and a roller, then when you do truss analysis, what is some of the things that you need to do? Well, you need to find how much each node is moving, right, in the x and along x and y, or in any two orthogonal directions. As well, you might need to know the axial force in each member and the amount of tension or compression, the stress in each member, and compare it against the strength to see whether any member would fail or not. Now, whether we can do all of it in one frame or two, let's take a look. So if I want to do analysis of the truss, as we'll see in my next video, one of the things you need are the coordinates of the nodes. And for providing the coordinates of the nodes, the easiest way is, of course, to have a what? To have a global frame that is fixed, and you present or record the locations of each joint, right? So for example, if I put that coordinate at point A, right, and say this is y global, then I have x global going through D like this, then of course here node A is 0, 0, node B is like 3 and 0, node F is like 3 and 4, and so on and so forth. So I can easily write down the coordinates of the points. Or if I want to show the amount of forces, so what is the force at node E? I say the force is 40 kilonewton along the x direction, or 40 kilonewton I, right? Or similarly, I can represent the forces at B and C as 70 and negative 70 and negative 45 in the y direction. So you see, or if I want to talk about the displacement, I say at node A, there is no displacement along x and y, while at the node D, there is no displacement only along y, x is free. So you see, I can easily present what? The boundary conditions, the forces, the locations of the nodes, and the orientation of the elements too. For example, I can measure this angle theta for member AF if I want, with respect to x-axis, right, by arctangent of 4/3 in this case, and get this. And so these are in the pre-processing step. Then we set up the equations based on these parameters and these numbers. And when we solve, as we'll see, as I said in the next video, the solution of the finite element is going to be the nodal displacement at each joint. So you'll find how much each joint is moving due to these loads and boundary conditions along x and y. So clearly x and y is absolutely sufficient for all of that. Now, why do we need the local frame, and what is the local frame in the first place? So local frames are not, first of all, there is not one local frame. We have a bunch of them. Okay, each member has its own local frame, or you might call it elemental frame, right? So there is not a unique one. The global one is one, right? But here you see it says a local frame to describe the relations between force and displacement in each member. So each member needs a local frame, right? So you have a ton of these local frames in this case, right? We have how many? We have like 9 of them in this case. Now, how would you show the local frame, right? And then why do you need that? So let's take a look here on this picture. So this is a member, like for example, AF at arbitrary angle theta with respect to the global x. And the nodal displacements for the two nodes of the member I and J are shown by UIX and UIY and UJX and UJY, okay? Where X and Y are written in capital letters to show that they are measured with respect to the global frames. Now, as you can see, the x and y here are parallel to the original x and y. But the local is, first of all, the origin of the local frame is what? Basically, as we'll see in 1D elements, the origin of the local frames are at one of the nodes, right? That's one thing. The other thing is the local frame is aligned with the member. So here I have a new frame, x and y, x small and y small, like this. And this frame, this local frame, is aligned with the member. You see the x of it is aligned with the member and y of it is perpendicular to member, and similarly here and here. So first of all, the local frame is rotated with respect to the global in general to align with the axial direction and the transverse direction, and the location of the origin of this frame is, as we'll see in the next example about 1D element, it is going to be for 1D element like the truss, it is going to be at one of the nodes. Okay, typically, for example, if it's left to right, most of the time it's the left node, or as I said, it's one of the nodes. So now why do we need this rotated frame, right? And this local frame, what is that? Especially in this case, the rotation matters much more. So why does rotation matter here? Because if I want to form the equations of force and displacement in each member, the force in each member is going to be along which axis? Well, clearly it's along the x local. It's along the member. So the force is along this member. What about the displacement, or basically the strain, the deflection? It is also along this member. If we assume all of these truss members are two force members, so each member is only under tension or compression, then everything is going to happen along small x, right? So if I want to write the relation between force and displacement, so I look at one member like this, as you can see, and then there are these forces applied here. So this is like F, and then it is what? It is I because it's at node I, and then small x because it's along small x, and then this is F, J, and X, which in magnitude should be the same as Fix, right? Because the member is at equilibrium, right? And then this member will be elongated like this, and the difference is called delta, right? Delta L. So initial length is L, the final length is L plus delta L. And the relation between delta L and this force is what? That delta L, as you know per solid mechanics, is the magnitude of this force, whichever one, doesn't matter, times what? Times basically the length of the member divided by the cross section and multiplied by the Young modulus. And from here, if you want to find an equivalent spring for, or a stiffness for the member, you say K equivalent, right, is basically what? Is the force F divided by the displacement delta L. So it is going to be A times E divided by L, right? So you see this K that you define, which is the local F and the local displacement, this is all along the local X, this equivalent K, which you can see over here. Okay, so our stresses and strains are in the local frame, everything else is almost in the global frame. So I need to have now that I know why I need them, I need to have a way to transform my information from one frame to another. And in this case, it's very simple. Why? Because if you look, the small frame is rotated with respect to the global frame by angle what? Theta, and this theta is clearly what? Counterclockwise. So the rotation is going to be a rotation Z matrix with angle theta, which if you watch my rotation matrix videos under playlist robotics, you clearly find out what a rotation matrix in 2D is about the Z-axis, and that is this guy here that you can see. This is a 2x2 rotation matrix for rotation about Z-axis and counterclockwise positive angle theta, and a similar thing is shown here. Okay, and the others are 0. Now, why is that? I'll tell you. But this T matrix here can take my basically local data and return them back into global data. And this data can be anything. It could be a nodal displacement U, or it could be an axial force, and then the force on the member, which is capital F, capital F. Right? Now, if I ask you what is the meaning of this small f, you can clearly tell me that's the axial force in the member, right? So this guy here. If I divide this f by the cross section of each member, what am I gonna get? I'm gonna get normal stress. But what about this guy, this capital F? Is that going to give me anything? No, right? That is not going to give me anything about the member, because that's not along the member. It's good when we are talking about the reactions at these nodes, and we want to find the reactions at these nodes. That's a global F, that Fx and Fy can be very good to determine the unknown reactions. But the small f's are good for what? For basically finding the stress in each member. So now I told you I'm going to explain the relation between the capital and small frames, or local and global frames, using this T here and this rotation Z matrix. Why do we have two blocks of 0? The reason is clear, because here you can see that the ux and uy are related to small ux and uy of node I, the same node, only using the rotation Z matrix, and they are not related to the J displacements, right? So when I say UIX and UIY, they are related only to what? To UI small x and UI small y, right? And that is cosine of theta, negative sine of theta, sine of theta, and cosine of theta. And by the way, these are abbreviations for sine and cosine. That's all it is. The displacements of node I are not related to displacements of node J, and vice versa. That's why I have these blocks of 0. Okay, and I'm going to explain this more in my next video on trusses. So you see clearly I need two frames, because different entities are described better about different frames. So I need a global and I need a what? Local. And there is another one which we call natural frame, and I'm going to show you that, which is very similar to the local frame, except for some small change in the variable. And why do we use that? I'm going to explain. But before I go forward, I want to show you that, you know, in finite element, we have problems that we use 1D elements, or 1D problems. We have problems that use 2D elements and 3D elements. So in these types of problems, or these types of elements, how does my global frame look like? How does my local frame look like? Okay, and then, as I said, the natural frame. So let's talk about those. So if your element is 1D, it's just a line like this, like you use in a truss, for example, or 1D heat transfer problem, or anything like that, then your global frame is what? The origin of the global frame is somewhere along the member, okay, or it could be outside the member. So you could, like truss, you could put it on the whole physical body, or you can start it here, right? Depending on which one is more convenient to you. And then local, as I said, the local frame is going to start at one of the nodes. Now, if my positive direction of x is to the right, then I start my origin of the local frame at the left node. So the beginning of the element is on the left and the end of the element is on the right. So now, what's the relation between the local frame and the global frame? It's very simple. The local frame, if you add to it the coordinate of the origin at which that local frame is established, you're going to get the global frame, just like that, right? Just like that. So if my origin of the global is here and the origin of the local is here, all I need to do is this distance from here to here, which is xi. If I add that xi to x local, I would get what? X global. Very simple. Now, if I go back to the truss example for 1 second, where are these local frames here, right? Where can I find these local frames? Let me show you some of those before we move on. So let me use a thicker marker, or maybe this color. So for global coordinates, this xy is good. What about local ones? So for member AB, the local one starts here. For member AF, again, it can start on A, but it is going to be rotated like that. For member BC, it is going to be like this. For member BE, it's going to be like this. For BF, it's going to be like this, and so on and so forth, right? You have one here, you have one here, and then you can have, for example, one here, right? So you see I have 9 local frames. Each one is starting at one of the nodes, and they are aligned with the member. Now, in this case, my problem is 1D. There is no rotation like truss. So although the element is 1D, here also the problem is 1D. The problem is not 2D like truss. So there is no theta in this case. If there are, then I can relate them, as I said, by this global, by this transformation matrix, by this rotation matrix T, as you can see. Okay, this is what can relate them to each other. Now, what is the natural coordinate, the third coordinate frame? Natural coordinate is very similar to the local. It is along the member, but instead of starting at one of the nodes, this guy starts at the midpoint. So here is L over 2. Small x equal L over 2. Here on the left you have x of 0, and the right you have x of L, where L is the length of the element. And this natural frame that you show it by the letter C is 2x over L minus 1. So when you plug in x of 0, you get -1. When you plug in x of L, you get +1. So the only difference is this entity, this C, changes from -1 to what? +1. That's all it is. And you might say, well, so what? So all you're changing are the limits, right? Instead of 0 to L, it's -1 to 1. Is there any advantage? The advantage comes when you later doing some integrals to formulate the finite element problems. And that's one of the next videos that I'm going to post for you, the formulations of FEA, right? We have direct composition methods, and we have integral methods, and so on and so forth. And the integral methods, right, like the Galerkin or others, many times you need to integrate something from A to B, like in this case from 0 to L, like strain energy or anything. And it's more convenient when you want to do that, instead you integrate from 0 to L, you integrate from -1 to 1. Why? Because you can use the Gauss-Legendre formulation, and you can calculate the integral of any function f in the range -1 to 1 by what? By just a few terms, where you calculate that function at some specific locations and multiply the value of f by some weights w and calculate your integral. So you see your integral is simply replaced by a summation with a limited number of terms. And the location of these test points and or evaluation points and the amount of weights and the number of these points is provided in tables that you can find online. So if you want to use 2 terms, 3 terms, 4 or 5 terms, and the more terms you use, the more accurate your calculation is going to be. You can see the location of the evaluation or sampling points and the amount of weights that you need. So that makes the integrations and the integration methods for formulations, that makes it quite a bit easier if instead of the limits of integral being arbitrary A to B or 0 to L, it's -1 to 1. So just wanted you to know that there is such a thing as natural frames or coordinates in elements, and I wanted you to know that. So this is the 1D elements, right? Now, if you go to 2D elements, right? In 2D elements, you can have what? You can have all sorts of shapes, but here I just talk about two major 2D elements that you see a lot. One is a quadrilateral. In this case, I simplified it to a rectangle, and the other one is a triangle. Okay? So in here, your global coordinate can be anywhere, right? Your global coordinate can be anywhere, right? It can be here. It's just one part of a surface. So here you have a surface, and you're approximating this surface by a bunch of these basically quadrilaterals, and they are not, again, all of them straight lines. Sometimes they have curved surfaces, and sometimes they have more nodes and so on. In this case, all you have are only 4 nodes. Okay, so only you have 4 nodes in this case, I, J, M, and N at the 4 corners, but there are other versions that will see higher orders where you get to have basically more nodes, 1 at the centers as well, and so on. And so your global frame could be anywhere, right? Your global frame, for example, could be here. But your local frames are located at the bottom left corner of each element here. And then, as you can see, so if the size of the element is shown by L and W, then the 4 corners have x of L, y of 0, x of L, w of y of w, x of 0, y of w, x of 0, y of 0, right? Now, your natural frame here is going to be at the center of the member, and it's going to have 2 axes. Now, this time you have Kc and you have eta, and the relation between Kc and eta and x and y are similar to the last case, but you have 2 of that. Instead of 1, you have 2 of that. And that makes also both Kc and eta to be what? Between -1 to 1. So this corner is both -1, that corner is both +1, and then these 2 corners, 1 positive, 1 negative. So in this case, if you have the double integral from, let's say, a to b and c to d of some function f of x and y, dx, dy, you can replace it by integral from -1 to 1 and -1 to 1 of what? F of Kc and eta d Kc d eta. Okay, and you have the double integration, and if this function is separable, then you can convert it to product of 2 integrals. Right, so this is what you have for the natural frame, for the local frame, and as I said, the global, which could be the origin of it anywhere in your 2D problems. And in this case, the relation between capital X and capital Y is similar, right? So capital X is the small x plus the displacement of node I, and capital Y is, or the location, sorry, x of node I, and this is the small y plus what? Y of node I. So you have this relation, but you have, again, 2 of that. So this is the frames for a quadrilateral element. Now, what about a triangular element? What do we have over there? For the triangular element, it's a little bit more complicated. The global coordinate can be anywhere. And here we do not really use local coordinate for this element. And the reason is the entities that we need, like the total area of the triangle, these smaller areas that I'll define in a minute, A1, A2, A3, the shape functions that we'll see again in one of our future lectures when I get to 2D elements, and all of those can really be defined with the X and Y capital. So we can just go with global frames for the triangular elements and define everything that we need. And we really do not need a local frame. Okay, instead of local frame, we can define a natural frame to replace that because we don't have it, but we can define a natural frame for a triangular element. And the way they define it is quite a bit interesting. So the way we define it is this: if you consider any arbitrary point P inside the triangle, and by the way, the triangle does not have to be an equilateral like this, it could be any arbitrary triangle, right? So you consider a point here and then connect the three vertices to that point, and that divides the total area of the triangle into what? Into A1, A2, and A3. So here A is the total area of the triangle. And the ratio of these three triangles, small triangles, over the big one is going to be defined as your Kc, eta, and lambda. And it's obvious that, of course, your Kc plus eta plus lambda equals 1, right? So it's not really like you have three frames here. You have three coordinate axes. You only have two. One of them is always depending on the others. But if we want to define a specific point, we need to use three of these, or at least these two. The third one is mostly for visualization here. And the reason it's a little bit difficult for the triangle is that the edges of the triangle are not perpendicular to each other in general, right? Like this one could be. So, and you have three sides, not four. So going just with two local frames like these two is not basically super easy and feasible. So what you will do is you define these three ratios as Kc, eta, and lambda, and as I said, all of these A1s, A2, A3, and A, they can be easily calculated by what? By the global coordinates of the edges, the corners, I, J, and K, right? The three nodes, as well as the location of point P. Okay, and let me just explain what does that mean. So based on this, what you can see over here. So if I go ahead and grab this point P and bring it and put it on node A. So drag this point and put it on node I. Sorry, not A, I. What's going to happen to these three triangles? Right? So if P is converged to point I, what's going to happen to A1, A2, and A3? Well, clearly A1 is going to be the entire A, and A2 and A3 are going to go to 0, right? So A1 is going to converge to A, and A2 and A3 are going to converge to 0. That means your eta and lambda are going to go to 0, and that means your Kc is going to go to 1. So this point here at node I is where your Kc is 1, and then your eta is 0, and your lambda is also what? 0. Okay? So that is that location, and then similarly, if you drag P and drop it onto J, A2 becomes 1 times A, A1 and A3 becomes 0. So at this point, that's where ratio eta becomes 1, and then of course Kc is 0, and your lambda is 0 as well. And similarly, if you drag P all the way to K, then your lambda, which is A3, is going to be 1 because A3 becomes the whole A, A1 and A2, which are Kc and eta. They go to what? They go to 0, as you can see here. Right? So each corner has one of the coordinates as 1 and the two other coordinates as 0. And you can see the direction that each entity is increasing, right? So at I, you have lambda of 0, and it increases in the normal direction to this edge to go to lambda of 1. In K, you have eta of 0, and it goes in the direction normal until it gets to the other corner, eta of 1. And at J, you have Kc of 0, goes in the normal direction until it gets to the other corner at Kc of what? 1. Okay? So this is how you define a natural frame for a triangular element, and you can use that way. Now, of course, here I did not include 3D elements, but if you're really interested, you probably can guess what they should be, right? So if I'm interested in a 3D element, then the 3D elements are going to be the hex elements, which looks like cubes, and then they're going to be tetrahedrons, right? These are the basic ones. Of course, there are other elements too, but for example, if I have a cube like this, then this cube is going to have, of course, what? 8 nodes, right? So the other one is like here. So you have 8 nodes that you can give them some names. And again, your global frame could be anywhere, right? Your local frame could be put on one of these nodes, like for example, maybe here, right? Like that. So that could be small x, that could be small y, that could be small z. Your x, y, z could be like this. And your 3 frame this time is going to be in the middle of the cube. So you have one here, and you have one there. So for example, these could be chi, eta, and what? Lambda. And in this case, these 3 are independent from each other. They have no relation like this. Okay, so if you have a hex element or cube element, that might look like this. And then if you have a tetrahedron, which is a triangle, and then you have basically 3 other triangles on the top, then you consider a point here somewhere like this. And again, here you're going to connect this point to all of the vertices. And this one is going to give you 4 smaller tetrahedrons. And then you might call them, for example, V1, V2, V3, and V4. And then the ratio of those V's over the entire V, the volume of the tetrahedron, basically can give you 4 parameters, right? You might add, for example, an extra letter to these, any parameter, right? You might call it phi or anything, doesn't matter. And then each one of them is going to be one of those ratios of those volumes over the total volume, and then sum of the 4 again is going to be equal to 1. So for this guy you need 4 of them, but one of them is going to be depending on the other ones. Okay, hopefully this video was useful to you and you learned a little bit about the 3 frames that we might use in FEA formulations, and I will see you in my next video. Thank you so much.